Hello everybody, and welcome back to another geometry lesson. Today, section 3.4, proofs with perpendicular lines. Although this section should really be called preparing us to do proofs with perpendicular lines, because it's giving us a lot of tools to help us with proofs, even though we're only going to actually practice one of them. Let's take a look at the first part of our notes. Assume for a moment you have a line and a point that is not on the line. What is the shortest distance you could draw to that line? Okay, so we have a point and a line, and we can make any segment connecting the two of them. And we need to figure out which segment will be the shortest possible route. So I'm going to give 3 examples. One case is that we could draw a line sort of going this way, connecting the two of them. This will be choice number 1. Another one, let's say we do sort of this diagonal line here, going from this point to this line, and this will be choice number 2. And another choice will be going straight down from the point to the line with this blue line. Number 3. And the question is, which of these is the shortest? We can very clearly eliminate option number 1. A point and a line don't have to have a horizontal line connecting them. But between 3 and 2, it's sort of tough to tell, really. But I will tell you this. Number 2 is going to be our winner. If I take a look at the measurements, without even knowing how well I drew them, this one is approximately 13/16 of an inch. This one here is approximately 14/16 of an inch, just a little bit longer. How did I know that? Well, because take a look at the shortest possible line. Line L seems to be going off this way, but this line, line number 2, almost crosses through it to make a right angle. This is an important thing to note. The shortest possible distance between a point and a line is a perpendicular line segment. If you want to minimize the distance, draw a perpendicular line segment. That is the basis of what we are talking about. So let's start off by giving the definition of the distance from a point to a line. Whenever we ask for the distance from a point to a line, we're asking for this: the length of the perpendicular segment from the point to the line. So it has to be perpendicular if we want to count it as a distance. There's another definition we're going to talk about, but we actually already talked about this. We talked about it back in Unit 1 when we did some constructions. A perpendicular bisector. So a perpendicular bisector is a line that is both perpendicular to the original segment and passes through the midpoint. So an example of this is something that we did way back when in Unit 1. Let's say I draw a 3-inch line segment here. Of course, I'm going to label this line segment. I'm going to give it the points A and I'm going to give it the point B. And in Unit 1, we learned how to make a perpendicular bisector. The steps were, place your compass on point A, put it at some point that's over halfway across. I'll use W. No, I'll use something a little closer. I'll use S. Draw an arc. Then repeat the process on the other side. Place your compass on the point. Choose the same letter. Draw an arc. And we said that if we were to connect these two intersections, we would find the midpoint M. And this line is perpendicular to the original. If I measure it out, let's see if we found the midpoint. It was a 3-inch line segment, and now that's a 1.5-inch midpoint. So that's perfect. Let's take a look at exercise 1, and then we'll do some more definitions. Exercise 1 is asking us to find the distance from point A to line BD. And the hint I gave is, remember the distance formula. With this, we have 3 distances to look at. We have point A going to point B. We have point A going to point C. And we have point A going to point D. And only one of them can we find the distance. Thankfully, we know now how to tell the difference. The only way to find the distance between a point and a line is using the perpendicular segment connecting them. So we don't care about the red or the blue lines, we only care about the green. So how do you find the distance between 2 points? Like point A over here and point C on the line? Well, we learned that there is a distance formula to help us. Quick refresher on the distance formula, folks. It's the one with the big square root. And it says the following. Take your x values, find their difference, and square them. Then take your y values, subtract them, and square them. Find the sum of these two and square root the result, and you'll get the distance. But I'm going to teach you something that's a little bit new with this. I'm going to remind you about how we can simplify a square root. So first off, let's plug everything in. I'm going to say -3 is my x1, y is my x2, so -3 minus 1 squared plus, I'm going to say 3 is my y1, and -1 is my x, or my y2. So we get the following. -3 minus 1 squared plus 3 minus -1 squared. The parentheses simplify out a little bit. -3 minus 1 is -4 squared. 3 minus -1 is just 4 squared. So this ends up giving us the square root of 32. Because -4 squared is 16, 4 squared is 16, 16 plus 16 is 32. Now, we could estimate this as a decimal. So if I plug this in my calculator, the square root of 32, we get around 5.66. So AC is about 5.66. But I don't want that. I want to remind you on how we can simplify a square root. To simplify a square root, here's what you have to do. You are going to split it into 2 other square roots, who, when multiplied, will equal 32. So essentially, I'm thinking of 2 numbers that multiply to make 32. Here's the catch. One of the 2 numbers has to be a perfect square. What are perfect squares? Well, it's funny that you should ask. Perfect squares are any whole numbers squared, and it's the numbers that you end up getting from those. If I was to show you a table of these values, it would look something like this. Some perfect squares include 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and we could keep going. My expectation for you all is that you have already memorized the first 12 perfect squares. If you have not done so already, I will be giving out a small handout to help you. So, looking at this list of perfect squares, what perfect square times any other number could equal 32? There's a couple of different possibilities, but I want us to find the biggest perfect square that's a factor of 32. 32 could be written as 1 times 32, or 2 times 16, or 4 times 8, and those are the only ways you can split up 32, I believe. Are any of these numbers perfect squares? Well, the biggest perfect square is 16. So to simplify a square root, split 32 into 16 times 2. So the square root of 16 times 2 is the same as the square root of 16 times the square root of 2. And since the square root of 16 simplifies to 4, the simplified version of the square root of 32 is 4 root 2. Again, if you want to simplify a square root, which I am going to be expecting you to try out, ask yourself, what perfect square could I break this number up into? In this case, 32 could be split into 16 and 2. But Mr. Strager, I hear you saying, 4 is also a perfect square. Why couldn't we break it up into 4 and 8? Well, I'll show you what happens. If you decide to split up the square root of 32 into the square root of 4 times the square root of 8, you end up getting the following. The square root of 4 times the square root of 8 is 2 times the square root of 8, which seems like a reasonable answer. But 8 can be split up even further. The square root of 8 could be written out as 4 times 2. So this becomes 2 times the square root of 4 times the square root of 2. Since the square root of 4 is just 2, it's 2 times the square root of 2, which gives us 4 root 2, the exact same answer we got over here. I'm not expecting you to be a pro at this right away, but I am expecting you to try this as often as possible. All right. Let's go back to our definitions, because we've got 3 theorems that I'd like us to talk about. The first is the linear pair perpendicular theorem. This is one of those theorems that sounds exactly like it is. The linear pair perpendicular theorem says this: if 2 lines form a linear pair of congruent angles, then the lines are perpendicular. What on earth does that mean? If 2 lines form a linear pair of congruent angles, then the lines are perpendicular. Let's say I have the following 2 lines intersecting to form a linear pair. In fact, I won't even make 2 lines. I'll make a line and a ray. This is angle 1, this is angle 2. I've said that 1 and 2 have to be congruent to each other. But remember what it means to be a linear pair. A linear pair means they add up to make 180. And if you're looking for 2 numbers that are the same that add to 180, there's only one way to do it. If they're both 90 degrees. In other words, 1 and 2 are right angles, so the lines are perpendicular. In short, if you ever have a linear pair where both angles on the pair are congruent to each other, you've got perpendicular lines. Next up is the perpendicular transversal theorem. This one's a bit more complicated. Let's say we have the following situation. We have a pair of parallel lines. You know they're parallel because I'm marking them as parallel, so we know for a fact we got what we're looking for here. And I tell you that this angle here is a right angle. The rule is, if you ever have a transversal perpendicular to one line, the transversal has to be perpendicular to the other line. Why? Well, for a reason we'll be explaining in a later proof. But for our definition, we can write down if a transversal is perpendicular to one of two parallel lines, then it is also perpendicular to the other line. Cool. Last but most certainly not least, let's flip the page to take a look at the final theorem of today. The lines perpendicular to a transversal theorem. And this acts almost, not quite, but almost like a converse to the previous one. This one says the following. Okay, we've got we got a pair of lines here. We don't know if they're parallel or not, but we do know that they are, in fact, both perpendicular to the transversal. The rule is, if you ever have two lines perpendicular to the same transversal, those lines have to be parallel by definition. So it's sort of the opposite. The perpendicular transversal theorem said, if they're parallel and one angle is a right angle, the other one's a right angle. This one says, if they're both right angles, then the lines must be parallel. So if two lines are perpendicular to the same transversal, then the lines are parallel to each other. Done and done. Let's take a look at example 2 and see if we can prove the perpendicular transversal theorem. As a reminder, anytime we're asked to prove a theorem, we are not allowed to use the actual theorem name. So this, the perpendicular transversal theorem, is the only theorem in the world we're not allowed to use right now. And this is a longer one too, although I thought of a way to do it in 5 steps that I'll show you here. But you could do it in longer. We're given that R is parallel to S, and J is perpendicular to H. These are our givens. What I want you to do is I want you to mess around a little bit. I want you to try things. Be okay with possibly getting this one wrong. It's a tough one, like I said. But by trying and making some connections, we will get a foothold to greatness. Pause the video and see what you can do. Hopefully you've had a chance to pause the video and try this one out for yourself. Let's see. We're trying to prove the perpendicular transversal theorem, which says if two lines are parallel to each other, and one of those lines is at a right angle to the transversal, in other words, perpendicular to the transversal, then the other line has to be perpendicular to the transversal. So really what we're trying to see is why this angle here is a right angle, or why it's perpendicular, I should say. The way to do this is as follows. First, the reason we're given is definition of perpendicular lines. Well, if we look back at our 3.1 notes, perpendicular lines, by definition, are two lines that are coplanar, that's not going to help us, and they intersect, that's not going to help us, to form right angles. So this tells us that angle 2 is a right angle. That's the important part here. We're also told that 2 is congruent to 6. Huh? Why would 2 have to be congruent to 6? Well, think less about the right angles and think about the parallel lines. You have two parallel lines cut by a transversal. How are 2 and 6 related? 2 and 6 are corresponding angles. So, this is the corresponding angles, but we have to decide if it's a theorem or the converse. In this case, since we're showing that two angles are congruent, that means we're using the theorem, the corresponding angles theorem. Okay, so what? 2 is congruent to 6. Well, here's the key. 2 is a right angle. 2 is congruent to 6. There's some theorem that we learned in Unit 2 about right angles being congruent to each other. Does anybody know what that is? What I will say is it tells us that angle 6 must be a right angle too. This is the right angles congruence theorem. This one we probably haven't really used much. It's a very abstract reason, but that's why we have our note card. The theorem says right angles are congruent to each other. So if you have two angles that are congruent to each other, and one of them's a right angle, the other one's a right angle. Wait a second. How do we use this? If we know that 6 is a right angle due to the right angles theorem, right angles congruence theorem, what does it mean? J and K intersect to form a right angle. Doesn't that necessarily mean that J is perpendicular to K because of the definition of perpendicular lines? The definition of perpendicular lines says two lines are perpendicular if they form at a right angle. Since 6 is a right angle, the definition of perpendicular lines can be used to solve this. This is the first time, and I want you to take note of this, that two different statements are given the same reason. This doesn't happen often, but with things like midpoint and perpendicular lines and a lot of other definitions, you're allowed to use definitions in different ways. This is one of them. This is one of those cases where the definition of perpendicular lines could tell us that an angle is right, or it tells that if an angle is right, then the lines must be perpendicular. Both are fine. Done and done. Last example. Example 3 asks us to determine which, if any, lines are parallel. This is an exercise in seeing if you have enough information to show that lines are parallel. I want you to pause here, but before you do, I want you to also label these lines C and D. As you can tell, they kind of got cut off on this side. I want you to see if you can decide whether there is or is not enough information to prove any of the lines in the diagrams are parallel. Err on the side of caution. So pause the video and try this out. Let's take a look at number 1. In number 1, what information are we given? We are given there is a right angle between V and Y. So we're told that V is perpendicular to Y. Is there any other information we can tell from the diagram? I mean, X and Y look parallel. V and W look parallel, but there's no theorem that says if two lines are perpendicular, then some other line is parallel. There's not enough information. So we could say not enough info to decide if any lines are parallel. And that's an okay answer. If there's just not enough info, don't assume that they're parallel. But let's take a look at number 2. For number 2, we know two things. A is perpendicular to B. A is perpendicular to C. We now have two perpendicular pairs. Is that enough to show that any of the lines are parallel? Well, I have a little theorem called the lines perpendicular to a transversal theorem that says yes. According to the lines perpendicular to a transversal theorem states that if two lines are perpendicular to the same line, they are parallel. And since A is perpendicular to B and A is perpendicular to C, then B is parallel to C. We've got it. We've got a pair of parallel lines. This almost resembles a transitive property when you write it out this way, but it's not quite because perpendicular, perpendicular, parallel. But you could think of it that way. The last one that we can take a look at is number 3. And number 3 is weird. We are told two perpendicular pairs. A is perpendicular to D, and B is perpendicular to C. And you might be tempted to say, oh, that means that C and D must be parallel and A and B must be parallel. But I have a little bit of a counter to that. Let me draw this diagram, but in a slightly different manner. Let's say that I drew, A and D were perpendicular, so I will draw A here and D here, like so. But then I'm going to draw B and C perpendicular to each other as well. I'm going to draw B going this way and, C going this way, got them mixed up, and B going this way. And you might say, Mr. Strager, this is a totally different situation, but it really isn't. We still have two parallel lines. If I cover up this one, you see the blue lines are perpendicular, not parallel. You see the blue lines are perpendicular. A and D are still perpendicular, but these lines and these angles have no relation to each other whatsoever. They don't interact. That's exactly what's going on in C, or 3. It looks a little bit different, like it looks like they could be parallel, but the lines perpendicular to a transversal theorem only works if two lines are perpendicular to the same line. We've got two lines that are perpendicular to different lines. Therefore, we are forced to say, not enough info. And with that, we are all set with 3.4. Thank you so much, everybody, and have a fantastic rest of your day.